All right. So let me start. Make sure my screen share is on. The slight delay. There we go. Like this video first. Okay. Welcome. So today we will be doing some docking. I hope to learn all of the steps in doing docking. And it's live instead of like an actual legitimate video because still some steps that I need to work out. But let's hopefully at the end, so there's probably going to be two parts to this video. One is actually starting with some of these issues that I need to still work out and make sure every component is ready for docking. And then the other part is actually walking through the entire process of how are you going to do docking. And you'll see all the mess that um, comes along with it, but hopefully it's not. Okay. So, that's more for like a video, but like a very general is ultimately what you want to have is I have an enzyme, it's a protein structure, and something that the enzyme degrades. Um, so, wait. Now let's open. Oh, I think I deleted those files. Okay, let me open just some example. So if I go to Rosetta docking, I have a bunch of structures, many thousand structures, and I'll let you know why there's so many. But if I open up and you can see this is a particular binding pose, right? So what's going on is the pedase enzyme, and then you're essentially docking this molecule where it's going to be where the reaction is catalyzed. So the active site is around here. Want to dock the molecule there? I guess there's two reasons why you want to do docking in the first place. One is to actually see the binding energies. So if you do this docking, if I open this file in NEI 00156, so 00156 is this one. So this is a PDB file, contains the protein, right? You see these are the XYZ coordinates of the protein. And then if you scroll down, you'll see some of the, so I'm using Rosetta for docking. Okay, so here's a ligand, right? This is the molecule. And then you see a bunch of these scores. So each of these tells you something about how the stock structure is. All right, is it good or bad? There's a scores. All right, you can see, for example, let's see, there's a total score somewhere. Anyhow, but there's a lot of scores. For example, this score is a picture of like during the docking process, what fraction of the Monte Carlo sampling moves were accepted. So saying 44% of these moves were accepted, which is not bad. All right, you don't like a 1% acceptance rate. A 40% rate is it's like half the time, about half the time, it's actually improving binding energy. Oh, here it is. Here's the total score. Okay, so this is the score, the Rosetta score for this protein and ligand system. Ideally, you want a low score, and ideally low scores correspond to native structures. observe in reality. But in addition to that, what you can get are these residue-wise scores. So you can see individual residues, and for each residue you have all of these separate scores. So Rosetta energy function is a combination of all of these components all added together with different weights on each one to form the total, right? So you can see, for example, for proline, you have a total score here. That's negative. But then some other scores, like asparagine here, that's positive. So that means, I don't know, asparagine is contributing to a bad energy, right? And you can see all scores are weighted scores and they're not the raw scores. So after weighing this linear combination, asparagine is contributing actually back poorly. So that could be a potential place of insight. However, this asparagine is just some random asparagine. Position 9. Let's see. It's ALA proline. Okay, so I think maybe. Oh, here it is. Yeah, it's a bit offset. It's a bit offset, but this asparagine is just like somewhere there. It's not really interacting with the ligand. Real interesting is if you actually look at some of those residues that are interacting with the ligand. My structure is PHL7. That's what I'm using a doc. So I guess of particular interest potentially alanine 63. Okay. I think maybe it's like offset by 1. Oh, really? And there's no phenylalanine. 63. Let's go to the 60s. Okay. That's interesting. So phenylalanine was actually forming a contact with the ligand. So it's like a special residue because this Rosetta docking protocol moves the positions of those contacting side chains. So it's a flexible docking protocol. And you can see the total score contribution here, the minus 68 point. And now here's comes the problem, right? If you were to make a plot like with this single structure, it will be completely disagreeing with the plot because they generated this plot on that's why you got these error bars, and they do clustering, and they look at the largest cluster, and they take the top or the lowest 10% of the structures of the cluster. So the intuition is you have clusters that you get when you do 10,000 different dock structures, and actually I think they actually did 40,000 dock structures. So you have 40,000 different structures. If you think about it in terms of probability, there are 40,000 draws from the probability distribution over atom coordinates of all 4,000 something atoms in your system. And nature likes to sample the low energy. So what you would also want to do is not just take the lowest energy structure of everything. It's actually to cluster like samples and find the most likely cluster. The most likely is the most populated cluster. All right. And within that most likely cluster, the lowest energy structures. So there's 2 layers of really your docked structure be as close as possible to what you would actually observe in reality is that there's actually no solved structure of this ligand protein complex. So really this model, is really the best we can get before a solved structure comes out. Okay. So yeah, you have to take a look at these scores, but also what's interesting is I use the D, which is the change in free energy. And this signifies sort of how good the interactions are when the protein ligand is interacting versus if they were completely separate. So this is saying, okay, if your protein ligand were to interact, that would have about a -6 calories per mole energetic. It's energetically favorable for those two things to interact because it's negative. You're decreasing. Um, Changing free energy is negative. So the interesting thing here also is that you can get a residue-wise contribution, right? And so if I go to that position 63, you can see a score for DDG. And you can see now that this is actually completely disagreeing with the results here. And the reason why that is the case is, this ligand is quite flexible. And actually, it's in a conformation that is not what I have it as. And how I know that is if you look at their figure, two rings, you'll notice it's not symmetrical. One side has two extra carbons and an oxygen at the end, and the other is naked here. So the side with the carbons is actually near these two rings here. And in terms of rotation, it's near here. But you can see the ligand in this pose is rotated 180 degrees. Not what this conformation is. Like if you were DDG values just blindly, you would get completely different than this one right here. All right. Now, luckily, they tell us their protocol to quite a lot of depth, in quite a lot of depth. So one thing that I found to be really helpful in this docking process is to add constraints. Because it's a super flexible ligand, you can see that there are many angles where the bond angles can rotate. And there's many, many degrees of freedom. Even, it doesn't look big compared to the protein. And you'll think it can sample actually, with each of these bonds here, you can rotate them. All right, this bond here you can rotate. And the stuff at the end you can rotate as well. That gives you 24, I think, degrees of freedom, which is of this particular ligand. Constraints are to make one particular atom close to the atoms will sort of interact with them in terms of catalysis. So in terms of constraints, there's a methionine, and then there is a phenylalanine here. So if I show both of these as licorice, all right, you'll see methionine. The two atoms are really key, at least for this system, but for your system, you have to figure them out from papers or literature. But for this system, this this hydrogen, backbone hydrogen of that phenylalanine, and the backbone hydrogen of this methionine participating in hydrogen bonds with this, this carbonyl oxygen. Now that in this pose, it's not at all participating in any far away, right? How do you encourage this atom to be close together? That is done through the use of a constraint. And so basically using that file will discourage this type of weird conformation where this atom is so far away from this area. Now, this sort of stuff you have to know from experiments or from a prior that you have on other enzymes. But what happens is this is the active site and this is the oxyanion hole. So the literature has said, yeah, I mean, this carbonyl is actually going to be participating in the mechanism of the reaction. You need these two hydrogens to be stabilizing this massive negative charge over here. So that's the model of the reaction mechanism. And, you know, if we are to agree with that model, the docking should basically should have all of these atoms at the appropriate distance where they are interacting. Otherwise, you're sort of sampling conformations that, you know, are plausible. Like this is certainly a plausible, but it's not really the conformations you care about. You actually want towards the kind of structures you do care about. Okay. At least in this case, I'm not doing any studies on like binding. You know, how good is it to bind without any constraints? Yeah, I mean, if you add constraints, you're definitely biasing the system towards a certain route, and so without constraints, anyway, tangent. In the other case, in any case, we can start the process. So what I have here, supposing you did the whole docking procedure and you have like 10,000 different structures, I want to actually get a distance matrix for all your ligands. And so what's going on here is that I am getting the of all the atoms in my ligand. And for each ligand, so I'm going over all the 10,000 something files. For each of those ligand files, or it has this a complete system, XYZ, and all the ligand coordinates to some master list. Okay, and then I get the distance matrix. So coordinates to distance matrix is something. Yeah, it's just a helper function that gets you the distance matrix between another ligand just by how far the coordinates are from each other. Now, this is important before you do this type of analysis, is that you need to make sure that these distances, pairwise distances, are actually comparable. In our case, it is comparable because the end is actually fixed in space, and it is the ligand that moves around. If enzyme were not fixed in space, you will need to center your enzyme. You will need to center your whole system based on your enzyme first, and then you do clustering on the ligand. You save a distance matrix, and the distance matrix is used as input to this cluster ligand function. So you load in that distance matrix. I'm using hierarchical clustering function. I am using distance threshold for that. So the distance threshold says you pick some ligand, XYZ coordinate stuff, you add another ligand to that cluster if the total, if that distance matrix value is within some threshold. And then if it's not within that threshold, I start a new cluster. And that becomes a new cluster center. Okay, and so what happens now is you have these labels. These labels are basically these, for each ligand, you have the labels tell you what cluster they belong to. And you can get your the frequencies of your labels. And this is what I'm plotting. I want to know what are the frequencies of all my clusters after I sort them. And also know the top indices. So what I'm doing is at the top label, so this is the most populated cluster because I'm sorting in descending here. I look at the most populated cluster, be my top label. Okay, to label my most populated cluster, I want to look at all of my indices, all of my ligand indices, where they have labels that are equal to the most, that are actually part of that. And I just print, I think, or I'm just writing out top ligands, this file here. Okay. Here's the part where I need to write some code. So sure, you can cluster your ligands, and sure, you can find the top, I guess, top cluster, the most populated cluster. And you've saved all those results in this file right here. And I actually have, 7NEI top ligands.txt right here. Okay. So what I need to do now is with all of these files, so these are all the ligands that belong to the most popular cluster. This cluster has 47 members. I need to plot. Okay, and not only that, I also need to get the structure with the lowest energy, and that will be used MD simulations. So I think the easiest one is possibly just, you need to think about these functions like modules, right? Reusable modules. So I can say get, let's see, what do I want to do with this function? I want to extract energies from one file. And in terms of energies, I actually want to look at the DDG. Do I want to look at the total Rosetta energy? To think about that a little bit, because so to get, so you can get both, and you decide later which. So we're gonna get energies. So here is going to be a PDB file. That's just going to be the path to the PDB file. And so we're going to return total Rosetta energy and so you can get this information file. But the issue with the score file, anyway, return total Rosetta energy, because I want to know, like, okay, it's fine. total represented energy in DDG for given PV. Okay. I think I have open. This is really bad, like stuff. So that's the DDG, right? So there's definitely a better way to do this. I mean, so there is a score file, right? There is a score file. If I scroll down to the very bottom, you can see there's a score. This is sort of not formatted in the ideal case, especially for the residue-wise DDGs. But I don't need the residue-wise DDGs, do I? Yeah, let's return the residue-wise DDGs as well. So that's going to be a really interesting thing. So basically, this is going to return a dictionary. And this dictionary maps strings, floats. It's going to be quite a big dictionary because I'm going to say f.read lines. I think this is a list and not a general. Let's see. You should always test your code on like small. So let's get the energies, and I always like to put like a default value in case. Sort of, yeah, you can just run it without no argument with no arguments. For example, this file. Let's copy path. I'm using Windows, so this is a weird backslash issue here. Okay, so I open that file, and you can see that these things down here are resi DDG, and this is DDG. I also sort of want to look at the total here, total score. Okay. This is a kind of inefficient way to do this. So you only care about those lines. Oh, sorry, line is not defined. Line starts with DDG. Yeah, this is kind of bad. Very inelegant. Very, very inelegant. They're all lowercase, right? Yeah. So total score space. Okay, so what happens? You do a split. Maybe you can first of any new lines in white space, and you get this splits this part right here. And then your value hopefully can be converted into a float. And then you have your result. That's a dictionary. I feel like I want to do it because, well, I mean, yeah, if it's default dict, what do you want? I mean, what's the default? 0? Yeah, I mean, default DDG is kind of sketchy. If you have a default DDG, it's gonna be a default. I mean, that doesn't make any sense. Okay. So that's all there is. I'm going through it backwards because I don't file. Results is sort of at the bottom of the file. I don't need to go through all the lines either. So this gives you a dictionary of strings to floats. All right. And so function I care about is I want to get the lowest one out of all of the in some list. Right. So get lowest. This is given a list of files, one per line. I want to get the ADB, get the file name lowest energy. And in terms of energy, let's just do DDG for now. If there's an issue, we will for that. So this is a seven MEI top. Yeah, so something about this file, right? Top lids. Yeah, I don't know. These files, this is a weird, maybe a weird Windows thing. It's having these backslashes, just super annoying. I don't know why there are even backslashes here. Let me. Oh, what's the doc string for this? Old, new, return a copy with all. Yeah, okay. I don't know if that's a. Yeah, that's a special character. A slash. Crazy. Okay, let me run cluster ligand again. So what it looks like. Okay. So this is 40 something. This should be new. Ah, beautiful. So all these things are forward slashes, which is great. And so now I can do this get lowest thing, right? Because you go through all these files. So and list as F for file or for PDB in F. You would get the I don't know if E is a oh yeah, don't use E. Get energies of that PDB file. And I want to look at the DDG portion of it. Float. So the best DDG so far, let's make it something ridiculous. And is less than the best. And then PDB. Okay. This doesn't return anything. Okay. So let's do it. And another, I actually, well, I don't know if I have TTDM here. Is it? Yes, it is. Yeah, so I like TQDM kind of, so how fast we're running things. So we're now get lowest. And well, I haven't even run get energies first, so see if it errors out. Oh, no, it didn't, which is good. And then we run get lowest. Okay. Yeah, okay, so I didn't do a strip. Beautiful. I'm doing about 100 iterations per second. That's pretty. It's important to look at that because I think about scale, right? If you were to actually get like 100 iterations per second, you can do 10,000 files in 100 seconds. Okay. So, but if you were doing one file per second, even if it was a fast on one file, it's going to take you forever. So that's pretty important. Okay. Okay, so this is really interesting. It got the 790i clean LG1 051. Okay. And then you can just look at that file and do that. Start MD simulations or whatever. Um, I want another plot. I want another function. This is making this type of plot right here. Okay. The unfortunate thing is I think Rosetta renumbers things. That's something to really be careful of. If you look at the file, alanine at 2, oh no, I don't think it did renumber. But you should always make sure and double check. Hey, I didn't renumber. Oh no, did it? ASN proline. See? Did it renumber? Well, let's see just how many you have. 259. That's a very low DDG, 259. But then your PDB file. Okay, so the PDB file ends at 259. Okay. That's really interesting that you have DDGs that are so low sort of elsewhere. And we can sort of see that if you plot so this is going to be operating on just one single PDB file again. And what was that? Get or plot bar graph of DDGs over all residues. I want to look at this get lowest again because it was 05199. Okay, so let's make that the default and just test this out. 199. Okay. What happens here is you need to do weird things with the dictionary. You get those energies from that function wrote. Now, I guess you could print this value, but be kind of sketchy. I know sort of it lands in 300. This is going to be basically I want to like get all these keys. So residue DDG at other position, and if your key is in energies, you're gonna put it in. Um, yeah. I don't really know what the best way is to figure out those labels. You know, you could have, because like, you know, when you sort these things, it sorts them this way, right? It doesn't sort them numerically. Oh, okay, whatever. That's what we're showing. Okay. VG for some particular structure. Okay, that's where things get really weird. It's so sparse, right? Oh, I know what you can do. Right. Some arbitrary, but like only append it if it's actually worthwhile to append it. And then the names can be here, right? And so does that make sense? There we go. Okay, I'm not saying any of the validity of any of these energies because this was run on like unconstrained docking, right? And it's really bizarre to have a DDG of like super negative at a residue that doesn't even participate in any interaction. Although, well, maybe I'm mistaken on that. But yeah, I mean, you can get a plot for one of them. This is just like plotting stuff, but the other plot is you would get, well, it would just be a script over the lowest 10% of your, and how would I do that? Let's see. So you would have a bunch of measurements per DDG, and then you would do that with uncertainty. The uncertainty is a bit weird because what you see in, and then you have an upper quantile and lower that you need to know from your data. But then you need to also fix those residues you track the DGs in, right? So let's leave that for now. So this is part one of the video, or of the live stream, is actually writing these functions. So this is 5199, but you can imagine, 00156. Just work. It's a completely different setup. 68. Yeah, I don't even know where 68 is. Why is 68 so good? 63 is not at all. The bar here is sort of flipped. Their thing is flipped. I don't really like this. I like just, raw. It's supposed to be negative. You want to go lower. This is kind of unsettling. You go higher and the lower the DDG is. Okay. Let me just git add. See, I don't know if I changed anything. Okay. So all this stuff is pushed. We've saved our work. We can close that now. Okay, so now let's walk through the entire process with constraint docking and all that. So for example, I want to show, for example, constraint docking, right? Yeah, currently there's nothing here. I want to show you currently where everything is. So I think it is on Cedar. Okay. That's going to take a while, right? Because there are too many files here. Let's just press this folder into I think there should be a recursive option, right? Recursion is the default. Oh, did I get the order wrong? Okay, so we're back. Apparently it's still streaming. So I don't know what happened with the stream, but I don't think I'm go. So I got disconnected. This is crazy. Okay, so Rosetta, docking. Okay. And if I do a cf7nei constraint.tar.gz, this will compress CST. Well, so CST here stands for constraint. Constrained. Okay. So this will take a while. All right, let's just go through the entire docking process again. So let's do it again on the 7NEI-CST, just to be complete of everything, and then we can do it on separate systems. And I want to like track of all the intermediate steps and where we can have time savings, because you want as little steps to be as manual as possible, but the parts that don't want to automate certain steps that should be manual. What I mean by that is like steps that you need to check and actually confirm if the program is running correctly. Just like any check, but maybe in the future we don't If you're really confident about those things, you don't need to do that. Okay. So the first step to the first step to docking of anything really is we're going to get our initial structure. All right, so I think I've actually tried this before. So we start with some molecule. To get the molecule, you can do the you can use a thing called the PubChem sketcher to like sketch your molecule out. Alternatively, you can use Avogadro. And then you actually draw, carbons and what. With these things, let's just see if it confirms it. Let's build pet. So usually if you want to dock something, you look at the chemical graph. Okay, it looks like this. And then you just build. So I don't have shortcuts enabled, unfortunately. And I don't want to adjust hydrogens. I want to do these sort of manually right now. So, and then carbon, oxygen. How come I don't have shortcuts enabled? Oxygen, carbon. So that's that carbon, this ring. All right, and then another carbon. You have carbon, 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 carbon. You can add these things in retrospect. And then double O. Was it with this one? So, luckily you can just select a bunch of things and delete it. So this is where I messed up. This is double O. And this is supposed to be, whoops, single. You can get a program that converts a smile string into this thing for you. All right, so you don't have to draw this thing out every single time. Yeah, I guess the only use case for that, if you want, is if you were to do docking for 10,000 different molecules and you want to sort of in silico figure out the DDGs for all these different substrates, then you should ideally have PubChem or something into a mol2 file. Okay, so go back to a single. You can skip this part if you want in the video. Just oxygen, and then carbon, oxygen. Carbon, oxygen. Okay. So this is like one subunit I got. I already have the two pet stuff. So actually we'll be in nice is doing it for one pet and actually doing the whole docking. So one pet means I terminate with this double O somewhere down there. I don't know where that should go, but yeah, molecule. Well, double. This is cis, and this is trans. Maybe you just did the trans because you wanted to fit on one page. So let's just do. Okay. Now, see this molecule that's drawn. What about the distance and all these things? It's kind of bad, right? So what you do is extensions, optimize geometry, and the covalent bonds their right distance. Okay. And sort of do this a couple more times. And you can see it sort of staying still like that. Okay. However, you haven't added any hydrogens. So you should be adding hydrogens. Now, pH, I don't think that we're just doing neutral pH. I mean, there's really nothing that's like titratable here, I guess. So let's just add all the hydrogens. And now, yeah, see, I was wondering why this was completely linear. That shouldn't be the case. It should be tetrahedral. So now if you do optimize geometry, you can see it won't change. Okay, and now you can see bend. This is really a molecular dynamic, step by step. Okay, so we've got the geomized file, save as, and we save it as mol2. So I think I already had the one pet mol2. So this is some second version. The reason why I wanted to do this here is I drew these double bonds and single bonds to make this mimic like an aromatic, right? Now, this original one pet I could using the PubChem sketcher and then convert it into mol2. So these carbons here are aromatics. Now, I don't know, so if I open this, you can see that even though it's sort of the same thing, it's not aromatic anymore. Right? Where's the aromatic? Let me see one pet.mol2. Was that a docking or docking? Yeah, you can see there's it's an aromatic. But then if you open the second version, it just alternates between single and double bonds. So yeah, that's the thing you have to be careful about. On Avogadro, if you just do single and double bonds, it'll actually give you single double bonds. It won't be aromatic. Okay, so we're going to stick with the original one pet. Okay, so what's the step in terms of docking? You have a mol2 file. You need to generate conformations of the mol2 file. to essentially same dimensional space. And I think I do that on the cluster. Oh, this is not even connect. Okay, it's connecting. All right. Okay, so you can see this one pet.mol2 was the exact same one. Yeah. Exact same one. Okay. I just need to confirm. 1.2, you have, minus 7223. Yeah, it's exact same one. Okay, before you actually do anything with this mol2 file, generate all the confirmations. It's nice to start your mol2 file in a good way. All right. So in this original protocol, they parameterize this thing through Amber. We could do that, but we could also just use the default parameterization that they give here. It's slightly different, but the parameterization is a bit of time. So if you leave this as is, we'll see what the results are. But the one thing I would like to change about this mol2 file is its positioning. So if you go on pymol, oh shoot, actually, I don't know if I can actually do this on my trackpad. Is you have a mouse, okay, and it's using that with the scroll wheel and whatever that to control. Do I have my mouse with me? Yes, I do. Here we go. Can't let this stop. Okay. Beautiful. My mouse. So one pet.mol, right? So you can go to pymol. And you open, let's say, on a dock to. So for example, docking, there's the 7NEI thing, right? Oh yeah, this is a corrupted file. Where should I find the thing I want to dock to? Let's just open one of these things, right? Okay. This is some random thing. Let's delete the selection. Whoops. Delete the atoms. Because I think that was in the wrong confirmation. Well, anyway, so what you want to do, that's the enzyme you want to dock to. You load in your molecule. And you zoom to all. You notice it's completely away from the rest of the. So you just change this to editing mode. Hold shift, click on the molecule here. And then holding rotate it. All right, with the left mouse button. And then holding shift, you can move it. So I want to move over here. Okay, and then let's rotate this a bit more. And then holding shift, I can move it. All right. So that's sort of where things are at. If you want to look closer, there is, so switch this back to view. I know actually for this system, there are two keys. There's tryptophan here and a phenylalanine here. And these two residues, what they're supposed to do is form like a clamp with this ring and sort of stabilize it. So if you look at their original conformation, right, this is sort of near here. So if I move this a bit, oops, sorry. So sorry about that. Change this back to editing mode. OMG. What did I? Did I add constraints somewhere? Okay, I hope I hope that was okay. So it was in editing mode. Editing mode. There we go. Okay, so let's move this sort of a bit closer here. Just undo that. Yeah. Somewhere like that. Somewhere like that. Okay. Now, if you think this is super sketchy, what you can do is measure the distance, right? Again, so actually what I'm thinking is this distance is a bit too far. Let's go back to viewing mode. There is a methionine, let's show as licorice. So let's do some measurements. So measurement from this hydrogen to oxygen, and then done. Do another from this hydrogen to this oxygen. And then I think there was a third distance. Well, anyway, let's just, go back to editing mode, select this, and you can sort of move this. Maybe rotate it. Ideally, you want it to itself, right? But I do want to also get it started in a pretty good initial position. This is 5 angstroms. Yeah, something like that. This is sort of an approximation of the initial position that you can have. And so let's save this. So save export molecule. I want to export the current state of 1 pet. All right, so I'll save that as mol2. And let's replace it. Okay, it's always a good idea to save your initial states as a PyMol session. Okay, so now this initial mol2 file, you have connectivity information as in the aromatic bonds and stuff like that. Okay. These things kind of changed on me, right? Any case, mol2 file that I want to generate conformers of. Let's rename that to just to make that a bit more descriptive. Okay. This is the OpenBabel command line that takes your things, input mol2 file and operations. And now this is for 1 pet. And so your RMSD cutoff might be, well, I think I actually replaced this with the right one. So yeah, you can tune this to how you want, but let's see how many this generates first. So for example, this output file, this was 100 numbers. Okay, this was for the 2 pet. And so I submit this job and it will just run. All right, it shouldn't take that long. After generating the conformers, I need to log into, so this, you should have something like locally that can do Rosetta, because you can do sanity checks, right, before submitting big jobs to the cluster. Okay, so this is some, I'm going to SSH into. Okay. To the Rosetta-based parameterization. What that means is this get Rosetta conf thing. Look at what this is, right? You have all the conformers in one file. 2pet.conf.mol2. And the clobber is supposed to be overwrite your output files. So, and by the way, figuring out, if you're wondering where I got all this weird information, it's from the Rosetta Ligand tutorial. So just walk through this tutorial with their original files. Okay, screen sharing was interrupted. Okay, so this is yeah, basically these two links give you a lot of good information. For example, this preparing ligands, right? You have all these instructions on how you do these things. PDB rotamers. Yeah. Okay. So this is where you're supposed to find. You know, this is where your mole. What is this? Mole file to params. Yeah. So you should have the conformers already because Open Babel does the conformer generation. Okay. So all I have to do here is going to be one pet. I don't know. Did I disconnect it now? One pet. Okay, and so with this one pet, let's check. Yeah. Okay, and it's done. Hopefully it's done. And 129 conformers. Beautiful. So that's actually quite fast. So it's this file right here. This is on gram. So let's transfer this file over. This one pet. Okay. All right. Now you have this one pet. So let's do bash. Get Rosetta conf.sh. Okay, there we go. It's done. And you can see we're centering ligands here. And that's important because that's really where you dock your thing. Or that's your initial starting position. So all your conformers have their initial positions there. Okay. Let's take a look at LG1 params. You can see, aromatics, bond types, internal coordinates, and then this links to LG1 conformers.pdb. Okay. Now this is where you should sanity check your stuff. So my docking script is, where's my docking script? It is rosetta.ligand.bash. Here's my docking script. So basically just run Rosetta scripts and it takes in two flags. So this is the options file. Okay, so this is your enzyme to dock and that's your ligand. All right, then you want to generate 10,000 structures. And then your protocol is specified in doc.xml. So in this is where your actual docking protocol happens. Now, I did a small ligand. Okay. And for example, if I change this number, so this is where your ligand is sort of, this is your box, your ligand box. If you change this to something ridiculously small, there's going to be an error because the box is too small. and your ligand is going to be going outside of the box. There's also these constraints, which I'll have to check in terms of the file, the atoms, if the constraints are actually good. But yeah, let's just, before that was 30, right? How you can determine that, like what size of the box should you use? If you open, for example, here, if you do a measurement from tail to tails, if you go from one end of the ligand to the other end, you can see the distance is like 11. Okay, so a 30 would be like covering this whole thing here. That's a bit too big, so I can change that to 15. There's a bit of a leeway here and there. All right, and I guess similarly for this, but I'll keep that at 20. So that's, you'll also see the oxyanion.cst file. This is your constraints. So this is going to differ for each one of your systems, unfortunately. This says, I want to restrain the distance between hydrogen of chain A, residue 132, to oxygen name is 06, of chain X, position residue number 1. So what that means, you should go to lg1.pdb for that. This is O. I don't even know if I have an 06 here. See, I don't even have an 06. That's trouble. So that's why you go back here. So what oxygen do you really want to restrain? You actually want to restrain with this oxygen right here. So you click on it and you say this is just O. What do you mean is just O? There has to be a name for that. Damn. I need to figure out the name for that. Yeah, okay, this one doesn't have anything. This is where docking gets. Whoops. Okay. I need to figure out what oxygen that is. Let's save that in docking. And let's open that up. Let me hide that. This 01. Crazy. Okay. So if you put an 06, there's try it. Let's try it. So bash try this, and there's going to be error. See? No, atom 06 was not found. Oh, okay. Why is this not resetting? Oh, then it's also crazy because I said 10,000. I wanted to do 10,000 structures. Oh boy. This is very interesting. Let me just go back and opening this up. Hopefully that doesn't do anything bad. Documents, IHM, Rosetta, docking, 7. Yeah. So you can see it errored out. So what is T? This response time is slow. Okay. This needs to be 01. Oh, by the way, what flat harmonic is saying between, you're centering at 2.5. And so between 1.5 and 3.5, that's the error here, you're going to get a penalty. Okay. I don't want to do 10,000. On local, we're going to just do 1. And let's see if this works. If it doesn't work, I'm going to cry. Skipping unrecognized atom. That's not good. Don't I have the params? I mean, you literally generated that PDB. Yeah, look. All oxygen stuff, all the parameters are here. That's wild. Okay. This shouldn't be happening. Yeah. I am specifying the parameters here, right? lg1.pdb. This means docking is working, but you might not want to trust the DDGs. All right. For example, generated 7 NEI clean. Oops. Okay. So a similar profile, if you look at like DDGs for residue 60 something, I don't think 63 was. 62? 62 or 63? 63, yeah. Not there. It kind of makes sense here, but I don't know how much to trust this. A skipping unrecognized atom. Oh, you know what's happening? There's an extra space. There's an extra space there. Oh my god. I really don't understand. This is very messy. Crazy, crazy messy stuff. What I suspect might be happening is somehow, like, the spacing is off. Let me just see if this will change anything. So this is lg1.pdb. Whoops. Unrecognized residue. OMG. You see? It's not doing the splits. It's actually doing it based on column stuff. This is absolutely insane. So if you shift this over, right? So you see if I shifted this over, it shifted the column LG1 over, right? So let me correct for that. I'm just being insane right now. Okay, let's see if the atom names are recognized now. The residue will definitely be recognized. Nope. Single ligand, you're adding rotamers, which is interesting because if I look at the options, okay, so this was false. If I set this to true, it's basically going to ignore those rotamers. Okay, so if I set that to true, it won't be generating any new rotamers. It will only use those existing rotamers. Nope, that's still the same. Okay, this is not really good because this is DDG mover is actually critical. So I need to figure out what the hell's going on here. If I think for 2-pet, it was fine. And let me try with 2-pet. So this was like 1pet.conf.mul2. Let me try with 2-pet because I've done this with 2-pet before. Okay. So this is 2-pet. And this is all the LG ones are now 2-pet stuff. Now let's do Rosetta ligand. Let's see if the warnings pop up again. Oh yeah, I think, what happened with this 2-pet thing was I did some weird amber parameterization and it wasn't good at all. Yeah, I need to figure this out. Yeah, you can see this is 2-pet normal 2. One pet. Yeah, not really sure what's going on. So let's convert this to this is LG1. This is now one pet. Yeah, all the things here make sense. I do not remember if I had that DDG error before. Maybe I had it before, I just didn't notice it. Okay. Let me see what kind of error. Okay. That really shouldn't be the case. I'm going to search this up. Oh boy. Single ligand rotamer library. Generate a mol2 and then generate a PDV using the rotamers. There we go. PDV rotamers file, but I would guess the atom names are subtly wrong. Yeah. Okay. So if I LG1.params